The Earth is covered in water. More than 70% of this planet is ocean. Yet less than 1% of it is safe for humans to drink. Every day, billions of people wake up surrounded by water they cannot use. Cities grow, populations rise, and freshwater sources quietly disappear.
Rivers are drying.
Glaciers are melting. Groundwater is being pumped faster than nature can replace it. By the middle of this century, water scarcity will affect more than half of the world's population. Not because water is gone, but because usable water is becoming unreachable. The oceans hold the answer. An endless supply of water stretching beyond the horizon. But there is a problem hiding beneath the waves. Salt. Ocean water is toxic to the human body. Drink it, and dehydration accelerates. The kidneys fail. Death follows faster than thirst ever would. For decades, humanity has tried to solve this problem. Desalination plants were built. Pipes, filters, and massive facilities rose along coastlines. They worked, but at a cost. They consume enormous amounts of energy. They damage marine ecosystems. They are expensive, complex, and inaccessible to many regions that need them most. So the oceans remained locked away.
Vast.
Useless. Untouchable.
Until now.
Hidden inside laboratories, startups, and experimental research facilities, a new kind of technology is quietly emerging. It doesn't rely on massive plants. It doesn't need endless electricity. And it doesn't fight nature. Instead, it mimics it. This technology doesn't just remove salt. It rethinks how water itself can be separated, purified, and reborn. If it works at scale, oceans would no longer be barriers. They would become reservoirs. Entire coastlines could drink what once threatened them. Deserts could turn livable. And water, the most basic element of life, could finally become abundant again. But this technology comes with questions. Can it truly scale? Can it be affordable? And what happens when humanity gains the power to rewrite the planet's natural limits? To understand the future of drinkable oceans, we must first understand why desalination has always failed us, and what this hidden technology does differently. For decades, desalination was seen as the answer. The idea was simple. Remove the salt. Drink the water. But simplicity ended the moment reality began. Traditional desalination fights the ocean. It forces water through extreme pressure, through dense membranes, against nature's resistance. Reverse osmosis plants work by crushing seawater until salt particles are left behind. The process is effective, but brutal. Pumps run day and night. Electricity consumption rivals small cities. And every liter of fresh water creates toxic brine in return. This brine is heavier than seawater. When released back into the ocean, it sinks, spreads, and slowly suffocates marine life. Entire ecosystems weaken near desalination sites. Fish disappear. Coral fades. Balance is broken. Then there is the cost. Desalination plants cost billions to build. They require constant maintenance, skilled operators, stable power grids. For wealthy nations, this is manageable. For the rest of the world, it is impossible. Ironically, the places that need freshwater most are the least capable of running these systems. So desalination remained centralized, exclusive, fragile, and worst of all, vulnerable. A power outage shuts everything down. A mechanical failure stops water instantly. A single breakdown can leave entire cities dry. The ocean remained vast, and humanity remained thirsty. But nature had already solved this problem, long before humans ever tried. Every day, the sun lifts fresh water from the ocean. Not salt, only water. Evaporation leaves impurities behind.
Clouds form.
Rain falls. Fresh water returns to land. No pressure. No membranes. No damage. For centuries, this process was ignored because it was slow, uncontrollable, and seemingly inefficient until technology caught up. Scientists began asking a different question. What if desalination didn't need force? What if it needed imitation? Instead of pushing water through barriers, what if water could move itself? New materials began to appear. Membranes thinner than a human hair. Surfaces that attract water but repel salt. At the molecular level, water behaves differently than salt. And that difference is the key. These new systems allow water molecules to pass freely, while salt is naturally rejected. No extreme pressure. No massive energy demand. Just physics. Some systems use sunlight alone. Others rely on capillary action. Water climbs. Salt stays behind. Small prototypes proved something extraordinary. Clean water could be produced quietly, continuously, anywhere near the sea. No massive plants. No centralized control. For the first time, desalination became modular, scalable, local. A village could run its own system. A disaster zone could create drinking water instantly. A coastline could become self-sufficient. This wasn't an upgrade. It was a redefinition. But innovation brings new consequences. Because when water becomes easy to access, control becomes the real challenge. Who owns the technology? Who regulates the water? And what happens when oceans become commodities? The solution was no longer technical. It was human. And the next phase of this technology would test not science, but society itself. The future of drinkable oceans is not theoretical. It is already being built. Across the world, scientists are testing technologies that once sounded impossible. Some of them use no electricity at all. One of the most promising approaches begins with sunlight. Solar desalination systems don't force water through machines. They invite it to move naturally. Dark, absorbent surfaces float on seawater. They capture heat from the sun. Water evaporates. Salt stays behind. The vapor is collected, condensed, and transformed into clean drinking water. No pipes, no pressure, no grid connection. Early designs were slow, but new materials changed everything. Engineers began using aerogels, ultralight materials filled with microscopic pores. They trap heat efficiently and accelerate evaporation dramatically. In some tests, a single square meter produced enough water to sustain a person each day. Then came graphene, a material only 1 atom thick, stronger than steel, more flexible than plastic. When perforated at the nanoscale, graphene becomes a perfect filter. Water molecules pass effortlessly. Salt ions are blocked completely. Unlike traditional membranes, graphene doesn't clog easily. It doesn't degrade quickly. And it requires far less energy to operate. Some prototypes operate with gravity alone. Water flows downward. Purified.
Clean.
Another breakthrough comes from biology itself. Scientists studied mangroves, trees that survive in saltwater environments. Mangroves filter salt through specialized root membranes. Only freshwater reaches their leaves. By mimicking this structure, engineers created biomimetic filters. These systems don't push water. They guide it. Salt is rejected naturally. Freshwater moves forward. No force. No waste. Then there are electrochemical methods. Instead of filtering water, they pull salt out of it. Using low-voltage electrical fields, salt ions are attracted to charged surfaces. Once captured, they are removed. The remaining water becomes drinkable. These systems are small, portable, and surprisingly efficient. Some can fit inside a suitcase. Combined together, these technologies change everything. They don't replace desalination plants. They decentralize them. Water production no longer needs megastructures. It can happen anywhere. A refugee camp, a remote island, a disaster zone cut off from infrastructure. Even ships at sea could generate fresh water indefinitely. But the real revolution isn't the technology. It's the scale. When systems become cheap, modular, and local, control shifts away from governments and corporations. Water becomes personal. And that creates a new kind of power. Because when survival no longer depends on centralized supply, societies reorganize. Borders soften. Migration patterns change. Conflict dynamics shift, but abundance brings its own dangers. If oceans become drinkable, what stops overuse? What prevents pollution from becoming permanent? And who decides how much water is too much? The technology may be ready, but humanity may not be. And in the next phase, the question will no longer be whether we can make oceans drinkable, but whether we can handle the consequences. Throughout history, water has defined power. Civilizations rose where rivers flowed. Empires collapsed when water disappeared. Control water, and you control survival. For centuries, freshwater scarcity shaped borders. It fueled conflict. It forced migration. It decided who thrived and who vanished. Now imagine a world where coastlines no longer fear drought, where the ocean is not a threat, but a resource. If oceans become drinkable, geography loses its grip on destiny. Nations built around rivers lose their advantage. Deserts gain new relevance. Islands become independent. Water no longer needs to be transported.
Stored.
Protected. It can be produced. On demand. This changes economics first. Agriculture no longer competes for shrinking supplies. Coastal farming expands. Food production stabilizes. Energy grids feel relief. Hydroelectric pressure decreases. Water-intensive industries relocate freely. Then cities change. Urban planning shifts toward coastlines. Megacities grow without draining inland sources. Population pressure redistributes. Migration slows. Conflict zones stabilize. But abundance always attracts control. Corporations move fast. Patents are filed. Licenses are restricted. The same technology that can free water
Can also monopolize it.
If purification systems are owned, water becomes a subscription. Access depends on contracts, not need. Governments respond differently. Some classify water technology as infrastructure. Others treat it as intellectual property. Some nations share research openly. Others lock it behind borders. The question becomes unavoidable. Is water a human right or a technological product? History suggests the answer is rarely ideal. When resources become abundant, they are rarely distributed equally. But this technology resists centralization. It is small. It is modular. It is difficult to control at scale. A single household can operate it. A village can maintain it. That threatens traditional power structures. When people control their own water, dependency disappears. Aid models collapse. Influence weakens. For the first time, water scarcity could stop being a political weapon. But abundance brings responsibility. Pollution becomes permanent when oceans are inputs. Waste management becomes critical. If contamination increases, purification systems must work harder. Nature will not absorb infinite abuse. There is also a cultural shift. Water has always been sacred because it was limited. What happens when it is everywhere? Does respect fade? Does waste increase? Or does value shift from scarcity to stewardship? This technology doesn't just change water. It changes behavior. And behavior determines outcome. The final challenge is not engineering. It is ethics. Because the moment oceans become drinkable, humanity must decide what kind of future it wants to build. And that decision will shape the planet for generations. So how close are we, really? Not decades. Not centuries.
Years.
Right now, pilot systems are operating quietly. On rooftops. On coastlines. Inside research labs hidden from headlines. Some are already producing thousands of liters a day. With minimal energy. Minimal maintenance. The remaining barriers are not scientific. They are economic. Scaling production takes money. Materials must be manufactured cheaply. Supply chains must mature. Graphene must move from labs to factories. Aerogels must become durable enough for mass use. None of this is impossible. In fact, the same curve that made solar panels affordable is already repeating here. Costs are dropping. Efficiency is rising. Every year, systems become smaller, cheaper, more powerful. The second barrier is regulation. Water is controlled by laws written for scarcity, not abundance. Governments move slowly. Technology does not. Permits delay deployment. Outdated rules block innovation. In some regions, it is illegal to produce your own water. That will change, because demand will force it. Climate pressure is accelerating. Glaciers are shrinking.
Rivers are drying.
Groundwater is collapsing. Cities are running out of options. When the alternative is collapse, resistance fades quickly. The final barrier is trust. People must believe the water is safe,
Clean.
reliable. That takes time. But trust always follows proof. And proof is arriving quietly. Entire communities are already testing these systems. Disaster zones are using them for survival. Ships at sea no longer fear running dry. In the coming years, coastal homes may include water generation, the same way they include electricity. Turn it on. Let the ocean do the work. But this is not a miracle solution. It will not fix pollution. It will not undo climate damage. It simply removes one limit, and limits shape behavior. When water stops being scarce, human priorities shift. Cooperation becomes possible. Long-term planning returns. But only if wisdom keeps pace with innovation. Because abundance, without responsibility, creates new forms of collapse. The technology will arrive. That is inevitable. The question is not whether oceans will become drinkable. The question is who controls the transition, and whether humanity learns from its past, or repeats it with better tools. One day, the sound of waves may no longer mean danger. It may mean survival, not because nature changed, but because we finally learned how to listen to it. Then don't forget to like this video, subscribe to the channel, and share it with someone who believes the world can be better. Because the ideas that change history only survive when people choose to remember them. Thank you for watching.